Dear students, we are back to the class of geometric design. We have been discussing about the alignment design, and in the previous interaction, we talked about the conditions where we have provided a flat cross section on a circular curve, and then we tried to see that what is going to be the controlling speed wherein the skidding or overtaking may take place at that particular location. And then we shifted towards the horizontal circular curve, and we discussed about the minimum radius that needs to be provided in the case. Continuing with this, in today's interaction, we are going to talk about again the radius of the horizontal curve, but for different category of roads, and then once we complete this, we will be moving to the super elevation design, and as per the time we will also see that how the super elevation is going to be implemented on a horizontal curve or before the horizontal curve. So, let us start with the radius of this horizontal curve and see that what are the various values which are going to be provided for different category of roads. Now, if we talk about the urban roads, as you can see on this particular slide, there are different speeds being given which varies from 20 kilometers per hour to 80 kilometers per hour, and then for the two values of super elevation, that is E, which is 7% and 4%, the minimum radius has been calculated. Now, the equation remains the same, which is R minimum is equals to small v square divided by g into E plus f, where small v is in meter per second, or it is v square divided by 127 into E plus f, where this capital V is in kilometers per hour. And as we have discussed previously, the value of f is a constant value being considered as per Indian Road Congress, and that is 0.15. Now, the only variation which is going to be there is either the speed, or for that particular speed the another variation which is going to be there is the value of small e, and that is what is being talked here as 7% and 4%. Now, when we are talking about these two values, I can just tell you that in the case of urban roads, desirably we try to provide 4% of the rate of super elevation, and if there is an issue, then we can go to a maximum value of 7%. Now, if we put these values here, say if we are talking about a case of say 50 kilometers per hour, then in this case V is going to be 50. So, you have 2500 divided by 127 into E plus f. So, if we are talking about 7%, then it is 0.07 plus 0.15. So, it is 0.22, and what we are going to get is a value which is very near to 90, and these values are rounded values. So, we are considering all these rounded values here. They have been rounded to something nearest. Now, same is the condition when you are talking about E is equals to 4%, and you can calculate these values by use of these particular equation. You can try by yourself and see that whether you are getting the values which are very near to these, and then how these have been rounded off. And of course, it is going to give you a sort of a practice session also. If we talk about the other categories of roads, say the rural highways or the 2-lane highways, multi-lane highways and expressways, then these three tables are giving us an idea. Now, in the case of 2-lane highway, we have 4 terrains, that means plain, rolling, mountainous and steep, and then within that we have a desirable and absolute minimum conditions, and using the same equation with the same values we have calculated these, and these are the values which are going to be there in the case of this 2-lane highways. So, these are the values which needs to be provided. If it is going to be less than this, then it means we have to see that if it is less, then restrict the speed. Now, in the case of multi-lane highways, we have two categorizations as far as the terrain is concerned. This is plain and rolling and mountainous and steep, and therefore, for these two again the desirable and absolute minimum values have been defined, but here you may find that exactly the same values which have been talked in the previous equation may not be working, and they have been provided on the basis of other informations available and have been computed and being denoted. The same is the case in the case of expressways, and where the design speeds which we have talked is can be up to 120 kilometers per hour with a minimum value as 100 and an absolute minimum is 80 kilometers per hour. So, for these three sets of values, again the desirable and the absolute minimum radius has been defined. And what you can see is that if you are talking about a 100 kilometers per hour speed and we are looking at a desirable minimum here, then in this case it is 700 meters. But if I talk about the plain terrain for a 2-lane highway and desirable minimum we are talking, which again is related to 100 kilometers per hour, it is almost half of that. So, that is a big difference which is there when we are moving from a 2-lane highways and then finally approaching the expressways. A vast flat radius has been provided on the horizontal curve, so that the vehicles can negotiate them very easily, smoothly, comfortably, and there is no issue of a safety in that. Now, this is another table where we are talking about the rural highways and the categorization of the rural highways we have discussed previously in the functional classification, where we said that these can be defined as national highways, state highways, MDR, ODRs and VR. And then again we have the terrain conditions being defined, and within the terrain condition, if you remember regarding the design speed, we had the ruling speed and the absolute minimum speed which can be considered, and considering those we have two values here, Rm and Am. So, there is an absolute minimum is Am or the ruling minimum is Rm related to those particular speeds. So, in that sense again the values have been computed, and what you found is that this is 360, 230 and then 230 comes here, and that is how the relationship is there, and then the whole set goes in this form and you get a new value. But when you talk about the mountainous and steep terrain, then here two sets of values have been given for both of the terrain conditions, and these two sets they are related with the altitude as well as the condition whether there is a snow or not in that area. And considering those things, the value of E is going to change. So, in general conditions we take E as 7%, but when you are talking about a no snow condition at a higher altitude, okay, so this is for higher altitude, it can be taken as 10%, and this is also we are talking when we are having a snow condition, then this is the value even at a higher altitude. So, that means when you are talking about snow, then this E is being considered as 7%, but when you are talking about no snow, then E is being considered as 10%, and going by the same equation which we have for R minimum, we are going to calculate the values, and this is what we are going to have. So, we have again the two sets within the mountainous and the steep terrain, and that is where we have to provide the values according to those. Now, once we have talked about this horizontal curve and the minimum radius of the horizontal curve, now let us start discussing about the super elevation which is required, because we are talking about a curved section, and on this curved section when we look at the profile, then this is the profile we are considering. So, you have a outer side here and you have a inner side on this one, and because there is a centrifugal force which is acting outwards, we are trying to counteract by way of raising the outer edge with respect to the inner edge, and this is one thing which is being defined as that this raise is E and the rate at which it is being done is small e. So, when we are talking about this small e, then there are design values of E which are there. Though I have given you some idea about these design values in the previous discussion too, but let us look at these values here. So, it says it is 7% in the plain and rolling terrain, and it is also being considered in the urban area as a maximum value. So, when I talk about the urban area, desirably it is 4%, but at a maximum level it can go up to 7% subjective. There is a requirement of doing so based on the local conditions. Now, when we talk about the altitudes, hilly areas which are bounded by snow, then it is 7%, but if it is not bounded by snow, again at an altitude, then it is 10%. On multi-lane highways and expressways, the two values are provided which are like 5% and 7%, and this is dependent on the radius in actual which is being provided at that particular location with respect to the designed minimum value. So, when we have a design minimum value on the basis of the terrain, on the basis of the speed. So, when we have considered these things and we have found out that what is going to be the minimum value, say 400 meter is the minimum value, and if we have provided 350 meters rather than 400 meters, then E has to be restricted to 7%. But say there is another condition where we have a 400 meters as a design minimum value and what we have provided is 500 meters. So, in that case, if we are going in this type of situation where there is a flexibility of doing so in an open country, then we can restrict the value of E to 5%. So, in that sense, if we talk about the values of E, then what we found is that we can have 4%, 5%, 7% and 10%. These are the values which are possible and they are dependent on the situation. Now, let us come to the design of the super elevation. That means, we have to see that what should be the value of E which needs to be provided. Now, when we are looking at this, the base equation remains the same, that is E plus F is equals to small v square divided by gr, where v is in meter per second, g is in acceleration due to gravity in meter per second square and r is the radius of the circular curve in meter. F is a constant value as 0.15 and what we are trying to find it out here is the value of E with respect to V and R. So, how we proceed here? So, if we are talking about this particular equation and considering that how the vehicles are moving, the vehicles are going to be a combination of fast and slow moving vehicles, big and small vehicles. The vehicles which are having the CGs quite very near to the surface and those which are having a CG quite up. Now, when we consider all of these type of conditions, then so as to tackle this particular thing with the help of E and F, what is being assumed is that 75% of the effect of the design speed, it is catered by the super elevation rate, whereas rest 25% is being thought of as being catered by the coefficient of lateral friction. Now, with this assumption we start working, that means, now let us first of all talk about the first condition of 75% of the effect of the design speed, and when we consider that in the step 1, then our V becomes equals to 0.75 V design and F is not being considered because we are trying to see that if all of the effect has gone to E, then whether the E is being able to sustain that or not. So, with this, if we put the values here, so what we are going to get is, we are going to get the calculated value of E denoted as EC is nothing but 0.75 V whole square divided by G into RC. Now, when we start putting the values here and trying to normalize it, then what we get is EC is equals to V square divided by 1.778 into GRC, and if we are putting the value of G as 9.81 meter per second square, then what we get is EC is equals to V square divided by 17.44 RC, and if we convert the value of V in kilometers per hour, then the equation becomes EC is equals to V square divided by 225 R. That means, if we have been given the speed with which the vehicles are moving on a road and on that particular road a curved section has been provided, which is provided with a radius RC, then we are going to get a value of EC. Now, once we have calculated this value EC, now the next step is to see whether this is okay or not. Now, what particular threshold value we are going to check it? We are going to check it with the design value of E, and this design value of E we have talked already. Depending on the conditions, we have these values in hand, and the most common value which is there is a 7% value. So, if nothing specific is being defined or you are not having an idea, then we are going to work with 7%, but if we have an idea that what is a situation in which our road is going to be, then we can consider either 4 or 10 or 7 depending on what conditions are being. So, if the calculated value of EC is less than this design value, then there is no issue. That means, EC can be provided and our work stops here. So, whatever is the speed and whatever the radius is there, that particular system is able to sustain the centrifugal force or the effect of the centrifugal force, because EC is less than the design value. But there may be a condition where the EC is either equals to ED or it is more than ED, which is the design value. Then we need to provide the value of ED because that is the maximum value. So, this maximum value is going to be provided, and once we have provided this ED value, now we have to make a check regarding the value of the coefficient of lateral friction, that is F, because what we have found is that whatever the speeds with respect to the radius of the curve are there, the E is itself not going to sustain that, and therefore, some of the effect is going to be taken care of by the factor F. So, when it is happening, we have to go to the step 3, where we are going to check the value of F. So, we will compute the value of F now, and we will check it with respect to the design value of F, which is nothing but 0.15. Now, when we are doing this checking, then we are going to utilize the complete formula rather than considering that 0.75 V, because now 0.75 V is already being consumed and 25% is being taken care of by F. So, with total value, we are going to work with the complete value of V rather than the part value of V. So, that means if you look at this equation, then it becomes nothing but that F is equals to V square divided by GR minus E, where E is nothing but ED, because that is the value at which it is being made constant. Now, once we put the values in this particular equation and calculate the value of FC, then this is being checked with respect to FD, and again the same criteria remains, that if this FC is less than FD, then we are going to provide FC, and still our system is going to sustain, because the combination of E and F is going to prevail and counter the effect of centrifugal force, and therefore, the process stops here. But if it is not a case and FC is greater than or equals to FD, then FD is to be provided, and once FD is being provided, now we have reached these two values to the maximum. And once we have reached these two values to the maximum and still some effect is being left which is to be countered, then we have to see that what is going to happen in this particular area. If the radius cannot be changed, then probably we have to change the value of V. So, we move to the step 4, where we are going to try to find out what is going to be the restricted speed for a given condition of R. So, when we look at this and going by the same equation again, then what we are going to get is that it is V square is equals to E plus F into GR, or V restricted is E plus F into GR and under root of that particular value, where E and F, they have been made constant at the design values, and RC is already given to us so as to take care of it. So, when we are looking at this, then what we found is that this is F into F plus E into GR under root, or this will be, if we are talking in terms of kilometers per hour, F plus E into 127 RC and under root of that particular value. So, you have this. Now, if you have a restricted value of V, then it is important that the speed control signs, they are placed in location on either side of the carriageway for the traffic which is moving in two directions, so that the drivers remain cautious, control the speed, and there is not going to be any hazardous situation at that particular location. Now, let us move and see that how this is being applied, and we are going to look at some examples in that direction. So, we have a two-lane two-way road, and on this two-lane two-way road, the vehicles are moving with a speed of 80 kilometers per hour. So, this is a capital V being given. The road is in plain terrain, and the radius of the circular curve is given as 500 meters. Now, let us look at the super elevation and whether the super elevation design value is going to sustain this or not. So, going by the same philosophy or the assumption that 75% of the effect of the speed is being countered by E as a step 1, which we discussed previously, what equation we have is, we have an equation as EC is equals to V square divided by 225 RC. This is what we found out. So, if I put the values in this particular equation, so we have 80 as V and RC is 500. So, what we get is 5.7%, and 5.7% is examined with respect to the design value of E. Now, this is a plain terrain. So, for a plain terrain, the design value of E is 7%. So, this value is less than ED, and therefore, we are going to provide the rate of super elevation as 5.7%, and our system is going to work fine as such. Now, let us see the another example. Here again we have a 2-lane 2-way road, but the speed is being given as 65 kilometers per hour and the radius is also being changed and it is 200 meters. So, let us see that what happens to the super elevation in this rate of super elevation in this particular problem. So, the concept is going to remain the same. So, we are going to work with respect to the 75% to the effect of speed as step 1 and we calculate the value of E c as V square divided by 224.5 R c and what we get is 9.4%. And because this is a plain terrain, so our E d is again 7% here and this 9.4% is greater than E d. That means now E has to be made constant at a value of E d and because there is some effect which is being left which is not being counted by E, therefore, we have to go and check for the coefficient of lateral friction. So, now we are going to step 2. So, when we go to the next step as per the design procedure of the super elevation, then this is V square divided by 127 R c minus E d because our equation was E plus F is equals to V square divided by 127 R. So, considering that what we have is F is equals to V square divided by 127 R minus E and because E is being made constant at A d. So, that value we are taking. So, when we put all of these values what we get is 0.096 which is less than the design value of F which is 0.15. Therefore, whatever has been the leftover effect of the was there because of the speed and the radius in terms of not being countered by the rate of super elevation has now been countered by the lateral friction and therefore, the system is again safe. The only thing is that we are working with 7% of the rate of super elevation and the coefficient of lateral friction is being restricted to 0.096 in this case, though maximum it can go to 0.15 and our work stops there. So, we stop here. Now, this is another example. Now, in this example again we have a 2-lane 2-way road with a 65 kilometer per hour speed, plain terrain. So, E is being defined as 7%, but the R is being reduced, is being made further half as 100 meters and let us see that in this particular case how the things are changing. So, when we are looking at this, so going by the same philosophy 75% of the effect of the speed is being taken considered here. So, we have E c is equals to V square divided by 225 R c and when put the values of V as 65 and R c as 100, what we get is 18.7% which is very high as compared to 7% which is the design value of E. So, that means we have to restrict E to E d is equals to 7% and because there is a lot of thing which is being left to be countered, we have to go and check for the coefficient of lateral friction. So, we are going to work with F c. So, this becomes our step 2 where we are going to work with this F c using the whole equation. There is no part thing being used here and we have V square divided by 127 R c minus E d. So, when we put the values here what we get is 0.26. Now, in this case what we found as this 0.26 again is quite bigger than 0.15 which is the design value of F and therefore, the F has to be considered as F d as 0.15, but with the combined effect of E d and F d still there is something which is being left which is not being countered and that is the reason that we have to move forward and now we are moving forward to the next step and we have to see that what is going to be the restricted speed in this particular case when the radius of the curve has been reduced to a low level of 100 meters at a speed of 65 kilometers per hour. So, now we have the same equation. So, we are trying to find out V r and V r is nothing but it is an under root of E plus F into 127 into R c. So, E and F are the maximum values. So, they are 0.15 and 0.07 and R c is 100. So, what we are getting is 52.85 kilometers per hour. So, the traffic was moving on this particular road. This is expected to move at a design speed of 65 kilometers per hour, but now what we have found is that we cannot allow the traffic to move at that particular speed, and that is what we are talking here. So, we have to restrict the speed to 50 kilometers per hour on this section. At the same time, we have to install the speed limit road signs at the appropriate locations to define to the drivers that you are reaching a hazardous location and you have to control the speed of your vehicle. So, this is how the super elevation needs to be designed. So, we have gone from one example to the another example to see that how it proceeds and finally what happens or culminates. Now, in this particular case we have been provided with the rate of super elevations for the urban roads. So, there is a bit of a issue of clarity. So, this is V of 80 kilometers per hour, this is for 60 kilometers per hour, this is for 50 kilometers per hour, and then for 30 kilometers per hour we have the curves, and on this y axis we have the value of E, which is going to the maximum of 7%, and because it is an urban road then 4% is the most desirable one. So, this is the line which can be there. So, if we are interested to see that if we are providing 4% and the speed is 60 kilometers per hour, then we go downwards, means what we get is the radius of the curve should be 400 meters minimum, and that is how we are going to design and plan for any of the road in the urban area. Okay, so, you have these type of curves. Instead of having the calculation, the curve can also be utilized to do that. Now, the another issue is that what is going to be the minimum super elevation. Now, when we are talking about the minimum super elevation, then this should not be less than the camber in any case. The reason being that this camber is being provided so as to drain the water and to make the carriageway dry as fast as possible. So, the camber rates have been provided in that, and that has been based on the rainfall intensity, that has been based on the type of the surface being provided. We have discussed them under the cross sectional elements in module 2. So, taking the values from there, we are considering these values. So, these needs to be provided and we have to take care of whatever are the situations in which these are provided, with what material they have been provided. Then there is a possibility that when you are not providing a super elevation, you are going to a camber, then this is defined as the minimum speed of the horizontal circular curve for which the super elevation is not required. So, the radius at which the super elevation need not to be provided and only the camber value is going to be sufficient. So, that needs to be calculated, and when we are calculating that, then we are using the same equation, that is R is equals to V square divided by 225 E, when we consider the effect of 75% of the speed, but only difference here is that this E is being replaced by C. So, instead of E, now we are considering C, where C is the rate of camber and V is the design speed in kilometers per hour. If you remember the rate of cambers which were there, they were like in the case of expressways or multi-lane highways 2 or 2.5%. When we talked about the various other type of surfaces, thin bituminous, thick bituminous, earthen roads, gravel roads and all, then we found that the values are increasing. So, it becomes 3%, it becomes 1.7%, all those values are there depending on what type of a situation we are in. So, you have to revisit and see that what are the various values of cambers and the given conditions of terrain, rainfall and type of the pavement surface. So, once you have got this value, you can calculate it. So, here it is being defined that for a given speeds ranging from 20 to 100 kilometers per hour, for the camber values of 1.7%, 2% or 2.5%, the radius, the minimum radius which is required is being calculated, and what we find is that if you are talking about 2% of a camber and the speed is 100 kilometers per hour, then this radius should be quite high and it should be 20 to 100 meters. So, if we have provided this type of a radius or more than this radius, then there is no requirement of super elevation, only the camber will be sufficient, but that does not mean that the camber which we are talking is like this. So, we have minus C% or plus C% camber, but when we are saying that when you have this particular radius like 20 to 100 or more, then we are providing C% as the camber and we are having the value of capital C, and that is how the curve is going to be provided. So, this is what is the meaning of this particular changeover. So, let us look at one of the example here. So, what it says is there is a horizontal curve of radius 3000 meters. So, a very big value has been given. It is a 2-lane national highway. So, when you have a 2-lane national highway which passes through a plain terrain, then the traffic speed can be found out. So, ruling value is going to be 100 kilometers per hour, but then that is also being defined here. The surface is thick bituminous layer. So, you are in a plain terrain where a low rainfall intensity is there and the thick bituminous surface is there. So, this is going to define the value of C because the rainfall is less and it is thick bituminous. So, we can work with 2.5% or 2%. These are the two values which are there. So, we can look at that. Okay. So, if you are going with this particular equation and say it is EC is V square divided by 225 RC. So, we calculate the value of EC and this value of EC comes out to be 1.48%. Assuming that we are going to provide a value of 2.5% as a camber, then the value cannot be less than the camber value. Say if we are talking about this 2.5%, if we are talking about 2% based on these given conditions, then we are saying that it cannot be less than 2%. So, what it says is that in this particular situation, the rate of super elevation which is going to be provided, this is going to be equals to the value of C percent based whatever for the given conditions which are there. Now, this is another example where we are talking about a national highway with a thick bituminous surface in rolling terrain. Rainfall intensity is more than 1500 mm per mm. Traffic is moving at a speed of 80 kilometers per hour. So, we have to calculate the minimum radius of the horizontal curve where the super elevation is not required. So, in this case when you are talking say the required camber for a given condition, say if we assume is 2%, then for the same equation if we put the values here. So, this value which we are going to talk here is V square divided by 225 C. So, C is 2%, what we get is 1425 meters. That means the minimum radius of 1425 meters should be provided, so that there is no requirement of providing a super elevation, only the camber is going to be sufficient and can be provided across the width of the carriageway. So, with this we stop our interaction now and we will be meeting in the next lecture to see that how the super elevations can be provided and they can be implemented in field. Till then, thank you and goodbye.